Okay.
I'm already sharing it. So how do we go to?
I think we'll have to share the screen again.
And, and show. Oh, I already am. So how do you project?
Let's see.
Yeah,
Okay.
there you go. Okay. It's okay if that's that right there.
Yes,
How do I move that? Can I move that or no? Is it a my?
maybe
perfect.
here. Yeah,
Yeah. Or can you minimize that?
I'll try. Okay.
That's fine.
Okay, you're all set.
Thank you so much.
Everything.
Doing well, doing well. How are you guys? I mean, they'll feed me every time I show up. You know, it works out.
Well, I know that you are just coming.
I mean, it is. So, no pressure. Things I'm not gonna ask about. The entire
Entire. I've never assembled all the experts in one room. It happens.
I haven't gotten invited. Did they start coming out with the invited?
Yeah, I don't think I started yet.
That's good, because it's hard, right? If I go overseas, I have to get an invite. Are you guys finding it? Yeah. Yeah. Sydney was awesome. No, it opened up. It's a lot better. Yeah. There's like the Olympics of my cross to be here for 4 years and I was thinking after that. Before that was.
Just good. To be talking South Korea.
Busan?
Yeah,
My cross meeting?
yeah, but
You don't
I
wanna go?
turned it down. It's just like I feel so guilty leaving almost the kids.
Yeah.
And I'm just like, hey,
No,
I
that's
had this
why-
great experience, sorry.
That's why I didn't go to M&M on there.
I know when I was tradition out of that.
There's 17. Take care of like the 13-year-old.
One thing that's, but right now it's a lot of like constant entertainment, constant struggle going on. Beyond them. And it's like, yeah, after a few hours of that, you just, I know you need a break. I know I need a break,
Right.
and that's not just being on the people 7 over the weekend.
Everybody wants to own, and they work 2 hours, and you have to I like this one. Yeah, it's,
Yeah. It's funny, like there was a critical threshold and nowadays it's loud, right? So, much smaller. They're very, classes are very, I like.
smash, but-
So if you look like the internet classes, they're like 100, you perhaps they're teaching, I don't know. The ones I never had was.
It was.
Right.
Look like people were.
With the coming, yeah. No, you should give it a minute. Oh, yeah. It's hard to leave the food, right? It's always like, you're slow going on. Ah.
The problem upstairs.
Too long. Like it. Oh, yeah. The wife told me it's free food. He's really, oh my God, so much. And he carries on like whatever's left. I don't know. But yeah, there's food, there's no.
Let's do it.
Hey, let's get started. I love the turnout. Thank you for coming. I have the great pleasure to introduce to you Raymond. He is working at Oak Ridge National Lab. That's where I used to spend my time in my former life. So we have actually collaborated typically on the same research project. So it makes me really excited of having him here. And also for me to learn the newest achievements of Ray. As you see from his title and the announcement, he's an expert in situ TEM materials characterization, which comes also with data analytics, AI. So all of these things are part of Ray's daily life. He said he's still using the instrument twice a week at least, which is impressive. If you think about all the leadership positions Ray is holding, he is a group leader at the Center for Nanophase Material Sciences. He's also a scientific theme research leader. And for a previous Energy Frontier Research Center, he was also a trust leader there. So Ray is very involved in interdisciplinary research, believes in doing research through big research teams. And so that's how we interacted in the past. He did his PhD at The Ohio State University in 2008. And then he applied for a fellowship, the Weinberg Fellowship at Oak Ridge in 2009, and that brought him to Oak Ridge, where he moved through the ranks, all the way up to where he's now. Ray also cares a lot about students. He's also, so for people who don't know, in Oak Ridge, we don't have students, so we only have postdocs and staff. But Ray is an adjunct professor at Georgia Tech and also joint faculty at the Bredesen Center at the University of Tennessee, Knoxville. So Ray also mentors students at different universities. He has a very impressive research record. He has over 170 publications with a very impressive age index of 60. And his work is has received attention through many awards, including 2 R&D 100 awards. I'm not going to read off his title. I'm going to just let Ray start. And again, thank you for being here. Thank you for being here. And I cannot wait to see what you have done the last few years.
All right, thanks, Nina. How's the microphone? Does it sound pretty good? All right, thanks for the wonderful turnout. I think Nina said it all, so we could just go home. She basically said my whole career in like 5 minutes. No, but I'm happy to be here. I'm happy to share some of the results that we've been doing. Like Nina said, my research efforts are in electron microscopy. And this is something I've always been passionate about since my undergraduate days when we do materials characterization, understand structure, property, performance relationships. But today I'm going to talk about how we can use in situ microscopy approaches to really look at fundamental mechanisms of phase transformations and kinetics and functional nanomaterials. And I'll start with a little primer slide of kind of motivating this. So the research that I'm going to show today is basically born out of our theme science. So like Nina said, I direct a quarter of the research directions at CNMS. I'm a theme leader for the directed nanoscale transformation, so you can slice it any way you want. But my spin on that is how we can use electron microscopy to shape new materials and understand functional behavior. So if you don't know who Richard Feynman is, might be quick Google on your phone, famous physicist from Caltech. He gave a speech in 1959 about there's plenty of room at the bottom. And a lot of people can use his hero type statements that he had in there to really motivate the science and what they want to do. One of the things was calling for the improvement of a microscope to be able to see at the atomic scale. But I took this a little bit differently. So one of the things, if you start to peel away the onion in this famous speech, he talked about direct write and how to basically put the entire Encyclopedia Britannica on a pinhead, which is pretty enormous feat because you guys aren't probably that old, but when I was a kid, we used to have that in our house, like big, huge stacks of books, right? So that motivates a lot of our research direction and how we can study materials down to the atomic scale, the fundamental building blocks, and how we can understand material properties that way. So this is a really important study that was published in 1990, Nature. Folks at Don Eigler and company at IBM wrote with an STM tip, a scanning tunneling microscope, where they can pick up and place individual atoms on the surface of materials. But there's a paper, a retrospective paper a couple years after that, where the title was pretty interesting. It said 35 atoms that changed the nano world. And perhaps the field of nanotechnology really kicked off with some of these ideas with atomic manipulation, how to build new structures from the ground up. Kind of like your Lego blocks, right? When you're a kid, how you can create really cool, like Legos or something like that, made out of a lot of different cool Lego thing. So fast forward a quarter of a century, Michelle Simmons at University of UNSW, she basically used the same idea to use a scanning tunneling microscope to place individual atoms and with the idea to make materials called qubits for quantum computing. So that's a long process, right? So there's some really fascinating phenomenon that happens at the nanoscale and how to structure these materials from the atoms on up, but it has a lot of problems. STM, if you don't know, it's a really surface technique. So you're not really looking at the 3D structure of material. You're not looking at the internal guts of what a material looks like. It's basically how you can manipulate the structure of the surface. So for some problems, it's really ultra high vacuum, low temperature. It's on surfaces. You have a limited range of materials. It's very slow throughput. As a matter of fact, if you can Google on YouTube, you can see The Boy and His Atoms or something like that. The IBM created a movie of how individual atoms, a boy can like throw a ball. Pretty interesting. So slow throughput, static, and 2D. So during the past decade, we've been doing a lot of work at the Center for Nanophase Material Sciences on how we can use different techniques to really understand how we can transform materials. All the way from the STEM, so this is atomic resolution STEM image, where you can look at how dopants are moving beam-induced in 3D. We can do a lot of direct write with nanoprinting with focused ion beam deposition. We can do a lot of directed crystallization where we can take an amorphous material, raster the electron beam, and create new structures, crystalline structures from an amorphous, so that's templated from a crystalline structure. We can also do some direct write. So if you have a liquid cell, Protochips is here in the audience. They make a wonderful product where you can do liquid cell electron microscopy. If you can have a reducible precursor chemistry, you can basically irradiate that area and create new logos, and your management is really happy with that. And then, of course, you can couple that with large scale simulations to understand a little bit further. So our laboratories and laboratories here in the AIF, you're really positioned very well to study a wide range of phase transformations in different environments, challenging environments in liquids, gases, ultra high vacuum, and solids. So this is what we're talking about with electron, ion, even scanning probe microscopy you can write. But a lot of advancements really come through the advanced control and feedback and automation, which I'll hit a little bit today. But the main focus is really what we want to do is understand how things transform the way they do, understand it and control it. And we want to be able to build structures that potentially can have use for quantum computing, spintronics, basically little nanofactories inside a microscope that can one day maybe stimulate the future generation scientists, engineers to think outside the box and come up with creative ways to make new device architectures. So what do material scientists do? Everybody's at different stages. Maybe some are undergraduates here, some are graduate students, some are postdocs, some are professors, some are senior professors. Here's what my take on material science do. So this is what we get paid the big bucks. This is what we get paid to do for a living. If you take a material, in this case is just a STEM image of graphene, what we want to be able to do is understand the structure and chemistry. We can do that with a variety of techniques. Of course, our cup of tea is electron microscopy. One, because you can have a technique called annular dark field STEM imaging, where you can take images of atoms and they're directly interpretable. So where all these white blobs are, hey, there's a carbon atom that forms graphene. But that's not it. I mean, this is just one part of the equation where you can synthesize new materials. What we really want to do is not only understand what the structure and chemistry is, we want to be able to modify materials for some application. So this is a case where we intentionally dope graphene with nitrogen, and we know this, we can take line intensity scans, or you can take EO spectra, or you can punch holes into it and create defects, functional defects that can be used for certain applications I'll get into in a second. So this is basically in a nutshell what material science, my perspective, what we do. And the idea is we always want to be looking forward to the next thing, what new or improved functional properties that we want to have of a material for service applications. So of course, I might be biased, but I think electron microscopy is an indispensable tool for that type of research. Otherwise, you wouldn't have these pretty images that are directly interpretable. Okay, so I'll be talking a lot about 2D materials. There's probably some faculty that do a lot of 2D materials here. You can synthesize this through CVD, you can exfoliate it, things like that. But materials that I'm talking about are graphene, boron nitride, some transition metal dichalcogenized like molybdenum, some MAXenes, titanium carbide out of Drexel University. But 2D materials have a really interesting gambit of material properties. So you can be semiconductor, you can have materials that are insulating, semi-metal, or having a metallic character and superconductor. So that's just like a little primer, but 2D materials are really integrating in our daily, everyday life because of the unique properties that happen at that length scale. So some of the applications that people are looking for are nanoelectronics, quantum materials, photovoltaics, batteries, capacitors, membranes, and catalysis. So here's a few examples where you can potentially use a 2D material to make a transistor. You can punch holes in graphene to have as a water desalination membrane. So something that you can transport water molecules through defects. And if you tune the size, you can basically reject all of the other junk. So this is really important if you want to desalinate the ocean, or if you have a lot of brackish water you want to get rid of, and have high purity drinking water for daily consumption. The other thing is MAXene. So you can have materials for energy applications for batteries and supercapacitors. And basically the structure lends itself very well to look at ionic transport through the different heterostructures that you have. So my motivation is, I kind of keep this in the back of my mind all the time. How can we tune the atomic structure of these materials? What are the atomic to nanoscale transformation mechanisms? And of course, I use microscopy to kind of point you to the right direction. And then are there new and unique functional properties that merge at these length scales? So again, microscopy is an indispensable tool. So if you like microscopy, this is a good talk for you. If you don't know a lot about microscopy, this is still a good talk for you. So you can learn a little bit more. Okay, so today I'll study three things. I'll basically introduce how you can use thermal heating to transform the edge heterostructure of a semiconductor. I'll talk a little bit more about our atomic fabrication efforts where we can use directed electron beams to create new materials controllably. And I'll talk a little bit about thermolysis, which is basically the breakdown of molecular species to form new materials. And all these experiments are done inside the microscope. So it's pretty unique. You can directly image it, you can heat it, you can put a bias on it, you can hit it with beams to do these transformations. So these are the 3 topic areas I'll talk about today. Okay, so what do we need? These are the elements that you really need to do these really cutting edge experiments. You need a microscope, right? You need something that's going to be stable. You need to determine what the operating voltage is such that you want to be able to either image it without destroying it or use it for the intentional purpose that you want to destroy it to create new structures. You need a heating stage, and I'm really happy that the folks from Protochips are in-house here because they help develop this design that basically you can put an electrical biasing holder and use these MEMS-based heating microchip devices to do really good heating experiments inside the microscope with really good accuracy, uniformity, and all that good stuff. The founders are in the audience right now, so if you want to talk to them a little bit more in development, they're here for your questions. So what we're going to do here is take a 2D material. This is moly diselenide. We've doped a little bit of tungsten, but that's not really important. What we want to be able to do is see what happens when we heat it up, you know, and I'll talk about applications in a second. So this is exactly what happens. You start to form holes, you destroy the structure of it, you start to form these little edge structures. So a lot of really cool stuff that we started to do when we played around with heating experiments in 2D materials. And I'll say why it's important in a second. So these big balls right here, we're basically forming moly carbide. And I don't want you to get distracted of that. This, I want you to pay a little bit more attention to what's going on at these different interfaces that we're creating, because I think it's pretty exciting. Okay, so what we've noticed in the microscope is that you can simply heat it up and you can transform the material. And the most obvious thing that you'll see is the formation of these little blobs. You'll see these little nanopores that form. But I want to direct your attention to basically what's happening at the atomic scale. I want you to see pretty closely that you have these atomic transformations that's taking place. With the microscopy that we do, we can see every single atom. We can identify what it is. And then we can get a better idea of how it's transforming and really use quantitative analysis to determine why and how, right? So a couple of things that we noticed right away. If an area is on a 2D material because you're transferring it from like a polymer like PMMA, you're going to have this gooey residue on the surface. Sometimes it's unavoidable. That interacts during the whole transformation process. So what I try to do is look at the chemical potential, and I'll get that a little bit more in time for folks that are studying thermodynamics as a function of time. So if we have a lot of residue that's built up, we start to have a propensity to form more of these ball-like moly carbides. So if we look at regions where we're transforming with medium and even low residue, we have different structures that form. So I'll explain that a little bit more in a second. So keep these pictures in mind, get a little bit of terminology. I'm going to talk about the atomic structure of 2D materials. So I'm going to say things kind of loosely about zigzag and armchair orientations. If you do 2D materials, you're going to know that how you're going to slice a material, you're going to have zigzag edges or armchair edges. I don't have it here, but you're going to have terminating groups, terminating atoms. So in this case, it's a zigzag. And then you're going to have moly terminated. So the purple atoms are moly. And the other one I can say, zigzag and sulfur-oriented. Or I can have these nanowires that start to form, which is like an atomic reorting process that I'm really interested in studying. Now, serendipitously, this was an observation that a PhD student had at Oak Ridge. Junhao Lin was doing a PhD from Vanderbilt, doing a lot of the work at the Oak Ridge with our microscopes. And one of the motivating factors he had is like, if I hit the beam, I can destroy it, right? So, and then I can create these metallic elements within a semiconductor. So it's pretty fascinating, published in Nature Nanotechnology, and now Junhao is a famous professor back in China. So he did a really good job doing this work. So it's something similar to that. So if you hear me use the terminology nanowires, it's basically this atomic reordering process that's an agglomeration of moly and selenium in this case. And then we might have a case where it's a different orientation, how it's viewed at the atomistic scale. Okay, so just keep that in the back of your mind. So what I wanted to point out here is just because we were able to see this at the atomic resolution, we can infer a couple of things. From theory, we know that if you hit these type of materials with electron beam, the chalcogen atoms are really easy to knock out, right? Because it's more prone to knock-on damage than the heavier moly atom. So what we say is here, we can calculate what the energy is to knock out a selenium atom versus moly, and it's a lot lower. Like it's 5.3 EVs versus like 12.3 EVs. So we can kind of make this correlation with a chemical potential. If I start knocking out the chalcogen atoms, I start to enrich the area with moly, and the chemical potential starts to increase. So this is basically our driving force, and I'll talk about phase diagrams in a second. So as we're heating it, either with heat or the beam, you're kicking out the easier to remove chalcogen atoms. You're creating these vacancies, and your chemical potential increases. So some of that happens where you start to form these carbides, but this again, this is where I'm interested, and I'll go a little bit, take a little deeper dive in that regard. So it's one thing to be able to see these dynamics. I'll kind of point to the reaction barriers and pathways in this slide. I'm sorry, it's pretty busy, but I'll try to make a point. If you're doing these experiments, and if you focus on this time series of ADF stem images, you can kind of see that the structure at the edge is starting to reconfigure, right? Because we're at such high resolution, we can know every single atom where it is and how it's transforming in the process. But even better than that, we can get with folks that have theory expertise that do density functional theory that can basically help us understand the reaction pathways and calculate the energy barriers. So when we're talking about transformation mechanism, we want to understand the reaction barriers, how easy it is for it to move, and also the pathway it takes to do that, right? So this is just a nice example that shows, I won't go into details, but other than the fact that, from our images right here, we're able to take density function calculations and calculate the energy that it takes to form at these different stages during the transformation process. Now, there's a desperate change in the time scale that we're doing here. We also turn to folks that do MD simulations. And from our STEM images, the time scale is pretty slow. But from MD simulations, we can kind of couple that with our in situ microscopy experiments to let us know that a little bit more detail about the bond breaking and formation process to form these reconstructed edges. So these are picoseconds time resolution, and then these are about tens of seconds time resolution. The answer is pretty much the same, but because we needed to collaborate with folks that do theory and simulations, we get a much better holistic view of what's going on during the transformation process. So if we let this play out, it's going to form the same type of edge right here. Now, that's just an example from experiments. Let's go to the nitty gritty of what we like to do in electron microscopy. We of course like to take these STEM images. So we've commonly seen 4 different types of reconstructions, zigzag terminated. So you have a zigzag orientation here, selenium atom right here. You have a single moly atom, and then this little nanowire that starts to form. Why I'm showing this and why this is so important is because STEM images can provide you only with so much. Again, the beauty is marrying the STEM imaging with the theory to understand a little bit better. So oftentimes what we like to do in STEM images is we have an idea of what the crystal structure is. We can create a structural model. We can run it through some code to do multi-slice image simulations to get an answer of what the intensities look like, and we can see if it's a perfect match. And why this is so important is once we have this atomic structure model, we can start to do some really fun stuff and start to tease out some of the properties of these edges that we just engineered in a 2D material semiconductor. So this is good. Experiments on top, simulations, they match pretty well. From that, we were able to extract the atomic structure model. And then now let's use theory again to understand what new functional properties that we have. So these are the 4 commonly reconstructed edges. Again, STEM, multi-slice simulations, the atomic structure model, and then you can calculate what the density of states are for these materials. Pretty interesting. If you take, for example, kind of point right here, this is your molybdenum. It's a semiconductor. So if I can reconstruct the edge right here, this edge has semiconductor-like properties as well. However, if I start to put a metallic nanowire that's enriched in molybdenum, I start to create this metallic element directly at that interface. And similarly, if I'm segregating a little selenium atom as well with this little grain boundary configuration, you can even create ferromagnetic type properties that are engineered at the edge. So I just want to keep in mind, start with a semiconductor, you can do atomic transformations, you can do atomic engineering, and you can get new functional properties that are highly localized at the atomic scale. So going back to phase diagrams, this is what we kind of talk about phase diagrams when we're thinking about this work. What is the energy of formation to form, what's thermodynamically stable to form these type of edge reconstructions as a function of our chemical potential? So what we can see in some of these calculations, I'll just point to the top. If you're kicking out the selenium atoms, the moly enriches. So the moly chemical potential increases. And so if this increases, this just gives us a thermodynamic estimate of what the most stable form is. And it matches quite well. We're pretty happy with that, pretty interested in that. So STEM is one thing, but it has also real world applications. So this is a really nice paper that came out around the same time from the folks in National University of Singapore, which they were doing MBE to basically grow 2D materials and changing the flux and basically how to tailor the atomic structure, much like we're trying to do it in microscopy. So I think the benefit of microscopy is you'll be able to see it. You can see the dynamics. You can couple with your friends in theory and understand the mechanism a little bit more and the functional properties. These guys were growers. They wanted to be able to understand that if you can change the flux, how you can create different edge structures. So there's a really nice match in what we're doing from in situ experiments to real world synthesis conditions. I just want to show that an example. But that's not it, right? We want to be able to understand and really predict that. So at that time, we thought we had something really interesting in the sense that we can see these transformations, but we also turned to our theory folks led by Ganesh, who's a group leader at the CNMS, and said, you know what? I have this workflow that's kind of think about all the different atomic rearrangements that we can have inside these transformations. And that's pinpoint which ones that we think we can synthesize experimentally and which ones are more energetically favorable. So that's what he did. Computationally screened hundreds and hundreds of atomic configurations using high throughput calculations and a little bit of machine learning too. So we came up with the type of edges that we formed originally experimentally, and then what are some new predicted edges that could be synthesized. So this is an idea to have, this fundamental discovery, how that can translate to real synthesis in the real world. And again, you have this phase diagram-ish like thing where you have the chemical potential and see which is the most stable edge. I just want to throw that theory slide in here to show that it's not just one or two off experiments. They could translate into some really important findings later on for synthesis. Okay, I won't go into too much detail, but engineering at the edge for atomic edge reconstructions is really important. It's been noted for a long time. You can change the properties significantly for photoluminescence, maybe some optoelectronic applications if you just change the termination and functionalize that. You can change graphene nanoribbons to have magnetic properties and so on and so forth. Okay, so I'm thinking about now semiconductors. I'm thinking about now quantum materials, quantum applications. This is really cool that you can see in the microscope, but can it translate to new technology that we can synthesize perhaps, or even artificially create with our electron beams? So if we start to think about these different edges, and I won't go to all the details, you can calculate what the character is. There's an interesting paper published not too long ago, but basically this says if you can transform the edge of these 2D materials, and they're thinking about making single atomic thick transistors, how you can change that to have different properties. So spin polarization, for example, how you can create heterostructures. Of course, this is a 1T prime phase for molybdenum instead of the 2H. But long story short, if you can change the structures, perhaps you can use this in future devices. And so some of the things that we're thinking about right now targeting is spintronic applications or even magnetic storage media, how you can change the local properties. And I'll get to that in a second. So I also do a lot of, instead of nanoelectronics or microelectronics, quantum materials, I also do a lot of catalysis as well. And this was something interesting that we thought too, is that how we can transform these materials, create defects intentionally for catalysis. So if you're thinking about catalysis for fuel cells, the winner material is platinum, and it has the best catalytic activity for the HER reaction. But you can take some of these 2D materials, and originally they're not catalytically active. So if you take a 2D material and pop it in a fuel cell to do an HER reaction, it's not going to be active. And that's because the basal plane is just extremely inactive for catalysis. However, if you start to dope it, if you start to modify it by creating defects, if you change the armchair configuration, it changes the zigzag configuration at the edge, perhaps you can increase the catalytic activity. So this is something that we're kind of spinning off, writing a few proposals now on that, is basically how you can transform these 2D materials to make it more active for catalysis. So I won't go to this in much detail, but this is known. People have known this that are thinking about alternative materials because platinum is really expensive. And that's why you see people like stealing catalytic converters and trying to harvest the platinum catalyst and reclaim it and try to make an extra buck on the side. So we can engineer the materials for improved catalytic activity. We can then computationally screen all the different edges. This is a really nice example, basically how the hydrogen atom can be adsorbed. What's the energy that requires to that? And we can use the change of free energy formation, basically come up with a descriptor, which one's pretty much active. I want to go to detail because I want to keep moving in the talk. So this is where I think it's interesting. I showed a little primer in the very beginning. I showed you that back in the 90s, right, you can use the STM tip, you can use electron beams. This is a large body of work that we're doing at the laboratory right now. I'll show you a couple of examples. This is one of the R&D 100 awards we got. But basically you can use electrons or ions as a good source because you can image it, right? With our microscopes, you can scan it. But if you have sufficient amount of energy, you can basically knock things out, right? And create new materials. So it's shown with the 2D material. So some folks are doing this where you can have a dopant of silicon inside a graphene lattice. And the idea is we want to be able to position new dimers, trimers, whatever structure that you want to make with these dopants in there. And the way you do that is you take an image of your graphene, you take the focus stem probe and you hit it on the carbon atom. It knocks it out of place and then something next to it can hop to that. So in your diffusion classes, you can learn about direct exchange mechanisms and all the hopping and all the activation energy barriers for that. So this is the way to create new structures at the atomistic scale. This is something I was interested in a while ago with liquid film microscopy. I showed you as a primer as well. You can take the electron beam, controlled with the right logo. You can use direct gas injection to create 3D structures from the atoms on up. This is also in 2D, in liquids, in 3D, but you can also do this in bulk in 3D in a 2D material, in a silicon sample. So these are individual bismuth atoms, and the postdoc that we had at the time, who's now at the Naval Research Lab, did an excellent job where you can take an image, you have these free floating dopant atoms, and you want to be able to create new structures like that. So the idea is to knock out some of the silicon atoms, and then if you're close enough, and you start to perturb the entire system, these guys start hopping around, and you can start to form like a really cool framework in that regard. And you can see this summarized in a paper they wrote in Nature Review Materials a couple of years ago. Okay, so this is the fun part. This is my postdoc that we just converted to staff. We want to be able to, if anybody does microscopy, you're taking a stem image, you're scanning left to right. It's a square raster scan. You can park the beam in a different location, but that's not automated and it's not controllable, right? Because there's drift and scan distortion and all that good stuff. So what we wanted to do is have this feedback control and automation system that's developed, that's integrated with our microscope to be able to change the scanning pathway, right? So if we wanted to carve out a material, just like in lithography, you want to move the beam in a certain direction. We made that possible with any of these microscopes. So we demonstrated this on the Titan that you guys have here in the AIF, but we've also done this on the neon ultrasounds that we have. Okay, so this is molybdenum sulfide. I'll talk about this a little bit more in detail. Basically, you can interface with the scan coils, and you can have a way that you can have a preformed idea of how you want to interact with matter. So we call these spiral scans. So we can raster the beam in different directions. You just tap into the scan coils in X and Y direction, hit the material, knock things out, falls on your detector, you can get nice images. But you can have this closed loop feedback system that says, okay, I'm messing with the system, let's move to the next step and irradiate a little bit more, dwell a little bit more to create what we think are like really cool nanopores with these edge structures again. So my postdoc at the time, really interested in saying, there's a little bit of crystallography going on here with the molybdenum sulfide. If you cut it along different zigzag orientations or armchair orientations, perhaps this can give us another free space that we can, like a little knob to tune if we want to really controllably transform these materials at that scale. So this is a case we came up with 3 different design paths: a circular scan, a square raster scan, and even a triangular scan. So these are some of the results. These are time resolved stem image during the entire process. So you can imagine spinning the beam, all the signals falling on the detector. These are feedback mechanism that says, okay, our defined point is we want to create a nanopore that's bound by these terminating functional edge structures. So when you start to form a nanopore, we tell the system to stop. But before that, we can just keep rastering, different directions. So this is really cool, but this is really what we're trying to do. If we're able to align the beam along certain crystallographic orientations, we can perhaps create structures with a high degree of fidelity. So this is what we did. We found that most of the reproducibility, we did a lot of these type of measurements for statistics, is basically if you did a triangular scan and then cut it along the zigzag orientation with the sulfur termination, moly termination, or even the armchair configurations. And you kind of see the armchairs right here. How does that result in your end product? And the idea is we wanted to create a nanopore bounded by those metallic and even ferromagnetic atomic edge structures. For what application in the future, I don't know, but it was just really cool to see that. So this is the most important thing that we came up with. So a high percentage of the time when we were cutting along this direction, we would kick out the sulfur atoms because that was a terminating group. Then you have this local enrichment in molybdenum, and then you can create these structures that we saw during the thermal treatment process. So we thought we had something pretty cool here. Well, so we're happy we just got published. Now I want to take it to the next level. Microscopy is one thing, to be able to image at the atomic scale is even better. But now let's get a little bit smarter about how we're doing things. So everybody's talked about machine learning or AI and ML in the loop in terms of material discovery, material design rules. We wanted to collaborate with folks like Sergey Kalinin, Maxim Zietanov, and Ayana Ghosh, who's basically come up with machine learning methods to post-process, I would say, and pattern match what types of defects start to form. So 2017, Maxime, at the time when he was a postdoc, published a really important paper that if you take a STEM data set with all these different defect populations, like vacancies that start forming, if you have graphene, you can create Stonewall's defects, so a little bit the departure from the 6-fold symmetry. You can take the time resolved data set and track it over time and really understand what's going on as far as the pathways. We wanted to integrate that in the microscope. So fast forward 5 years later, the only way this was able to work is a teamwork. We had a postdoc at the time who's now staff, Kevin Rockberry, who's really good at CNC machining and really thinking about ways to interface instruments to create new things. He had a really good idea of how you can control the microscope. Maxim had a really good idea of doing these neural networks to basically pattern match and identify. And what we're really good at these beam strategies. So if you put all these 3 elements together with a good scientific vision, how we can use AI and ML for control and automation. Now, I will mention this is only available if you have a microscope that's open that you can tap into with Python, for example. A lot of vendors these days, closed loop system, you can't really crack the nut, you really can't crack in there and really tune things the way you want it to. And I kind of think about that as modern cars, right? If you want to work in your own cars these days, it's really difficult. Pop the hood and you're like, oh my God, there's all these panels, I don't know what to do with it. So very much the same way, but we're very fortunate with the instrumentation we have. We're very fortunate in the sense that we know what we want and we know how to do it. So basically you have this data stream. I'll kind of walk through this and I'll get to the coup de grace right here. So if you take graphene, for example, you have pretty noisy images. You can use machine learning to basically denoise it. You can use machine learning to then identify where these atom positions are. So this is the coding and the classification. So when you keep hitting with a beam, you're going to start moving things around, knocking things out, and creating either pores or Stonewall defects or just distorted lattice, whatever you need. So you can have this 6-fold symmetry that can change into 5-7 type rings. So you can match that really quickly. But the most important thing, the most important advancement that was made possible by Maxime was to be able to decode the images, but also determine atomic locations. And this is really important when you're thinking about atomic fabrication in the general sense that if you have a stable instrument, if you know where to shoot the laser beam or you need to know where to shoot the electron beam, you need to have atomic coordinates, and then you need to tell the machine to hit it in those coordinates. So this is that beam strategy that we're pretty used to doing. So another paper that we're working on, so this is just a demonstration workflow that is possible. Another paper we're working on is, remember I talked about the edge reconstructions to have some new properties. I think I have to play through here, but with the same idea of knocking out the easier to remove sulfur atom, we can do something like this. So what you're seeing is frame by frame, this happens with machine learning. Frame by frame, I can get an atomic resolution image. Frame by frame, I can tell you by this machine learning classification where all the atom positions are, and then color code that with whatever defects that are forming. So it took a while for my postdoc to come up with the training models on how to, for molybdenum sulfide, to figure out which are defects that you're forming. But if you look closely, this is pretty interesting what's going on. If you take a 2D material, the molybdenum sulfide, the bright atoms that you can see quite readily, you can see it a little bit better on the laptop. The bright atoms are the moly, the less intense ones are the sulfur stacked on top of each other. And what you're starting to see right here is you have a collapse in your lattice. What we're doing right now is we're taking images frame by frame. We're telling the electron microscope to knock out the chalcogen atoms to create what we call these single vacancy line defects. So it's like you have a sandwich structure and you're removing the bologna and the bread is coming together. What I think is really important about this is now we just change the properties at the atomic scale, at will, and under our control, and it's automated. Pretty fascinating stuff. So I can envision something like this where if you have a semiconductor and you're trying to scale down a device level, scale down to device level, maybe making single atom transistors, so on and so forth, you want to be able to create these little ohmic contacts. So when I collapse the structure, these two layers of moly atoms that start to come closer and closer together, they're now metallic. They're metallic elements that we built in there from a semiconductor. I'm pretty excited about that. And I'm also very excited about these little nanowires that form too. So I'll show you an example of that, how you can change the scan direction instead of just kicking out the chalcogen atoms. I can then do the spiral scan, all automated. I think that's pretty interesting. I don't know. I see some optimism in the audience. I see somebody sleeping, but that's okay. This is pretty cool. Anyway, so the idea that we want to go with this a little bit further is Moore's law is coming to an end. Oh my God, you know, it's like, what was that turn of the century when, oh God, what year was that? 2000, right? Remember the world was going to come to an end, 1999 and 2000, when all the computers, if they reset the clock. But anyways, this is a real deal. The idea, if you want to make microprocessors, to put tons and tons of transistors on a smaller and smaller area. This is not going to solve the world problems, but it can at least give people ideas of what you can do at the atomic scale. So this is a really nice image, basically, that says, back in the day, you know, this is the scale of a transistor on a microchip. And then if you go to 2022, 2023, I know this is a cartoon representation, but now we need to be thinking about how we could create processors on the levels of single atoms. So maybe this is a pathway that I don't know. That's beyond my level of expertise. So I'm going to skip a few slides because of time constraints. No, I'll talk about that. So I talked about atomic transformations, directed atomic fabrication controllably with machine learning, with AI. Let's talk about thermolysis. A lot of folks right now are interested in quantum materials. Hey, you can take 2D materials, stack them on top of each other, change it to a angle, create new interesting properties that start to form. Again, we're using the system from prototypes where you can do really stable heating all the way to 300 degrees. We want to understand a little bit better about the synthesis science. It's really important that we want to study. So if you take a precursor that people use in CVD growth, you can make a suspension, put it on a heating chip, quite easy to do. You can just drop cast it. But if you want it thinner, you can drop cast and spin coat it. And then you heat it up. You heat it up and you can visualize things out at the atomic scale. You can see how these basic building blocks of a two-dimensional material start to form, which is pretty exciting. So you have these atoms start to coalesce together, and you get enough time, get enough heat, then you're going to start to transform these 2D materials, van der Waals heterostructures on top of each other, rotate it. So we did many experiments. We wanted to see temperature effects. We wanted to see substrate effects, like if you have like an amorphous carbon film or if it's freestanding, and we kind of mapped out how you can form layer by layer. This is where the interesting material science comes in, because probably, I don't know what you call it here, MSE 200, 201. When I went to school a long time ago, it's called 405. Intro to material science, we talk about grain boundaries. And we talk about what wonderful properties you have on that. Well, this is something now people can see in real time at high spatial resolution, how a grain boundary coalesces. So this is just one snippet in time that basically shows how two grains that are different orientation need to reorient themselves and have a grain boundary, first of all, and how you can coalesce. So this is a really important phenomenon that we can manipulate in material science. And then we can understand how these atoms can start to grow on layer and layer and layer. So I won't go into too many details because I'm kind of pressed for time and I want to show you some other cool stuff. All right, this is a quick summary. I showed you that we can do atomic resolution STEM imaging to study transformations all the way to atomic scale. We talked about the thermodynamic properties that happen or the behavior, why you preferentially form one edge to the other, and it's all linked to chemical potential. So your free energy diagrams that really hits home with some of the stuff that we're doing here when you talk about phase stability and what new phase starts to form. But I think this is the last two things that I want to close this talk with is, you know, we want to be able to provide pathways to create structures at the atomic scale. Because if we're pushing more and more down to this Moore's law, or we're trying to tease out new interesting properties at the atomic scale, we need to be thinking at this length scale. And then also, obviously, the machine learning is starting to be a big impact in everybody's life. And it's even finding its way to the laboratory. It's even finding its way to the STEMs. So this is pretty much my summary. With the last few minutes, I want to talk about some really cool stuff that I think could be the future of microscopy. And this is just personal bias. So I do a lot of in situ microscopy in liquids, in gases, solid state. I kind of feel like this is what we like to term lab in the gap type experiments where, you know, sometimes in microscopy, you want to look at the surface structure, the morphology, the chemistry with whatever technique of your choice, SEM, EDS, STEM, EDS. But you can really do some one-off crazy experiments that can get you really cool answers. So this is something that's pretty important in terms of new holder development. These are really old holders. We have cryo holders. We have the MEMS-based biasing holders. We have nano indentation holders, tomography holders, liquid cell, cryo transfer, or sorry, not cryo, just regular transfer holders. But I think the main challenge has been solved with companies like Protochips, for example, that's in the audience. You can be able to do some really cool stuff in liquid and gases. We were actually the first to publish the in situ electrochemistry to see dendrites. Of course, Nanoletters published the competing group at P&L in the same issue, but we submitted and it got accepted first. But this is the first time we were able to see lithium dendrites nucleating and growing at interface in real time, high spectral resolution inside the microscope, inside the Titan that we have here. Obviously, you see the potentiostat, microfluidic delivery system. You can do a gas phase analysis. If people in the audience are looking at materials in extreme environments, for example, you want to heat things up, change the gas, jet aircraft engines, for example, or anything that's exposed to different nasty gases or high temperature oxidation. Show a little bit about the solid state transformation that we can have here. I did not know Protochips was going to be here, but this is a primer. This is going to have a big impact on catalysis. And when you're thinking about in your PhD and beyond that, and you know, when you're transitioning to the next stage in your career, you know, what are some meaningful problems that you want to solve, right? Material science, you're given the fundamental of you know, then you're dangerous, right? What you want to study. I tend to study things that I think can have a transformative impact in people and lives. So a lot of things that are going right now that you hear all the time is, okay, global warming. You're gonna have carbon capture. You want to be able to develop new materials that can sequester carbon dioxide from the environment, store it somehow. You want to have catalysts that basically can speed up reactions and convert new types of chemistry. And now the biggest thing right now is hydrogen storage. Maybe it was a big thing a long time ago too, but it's hitting a thing right now with electric vehicles, fuel cells, for example. We want to have hydrogen storage materials that can do that. And I think perhaps the electron microscope can behave or help understand some of these opportunities. So now you can look at things in high vacuum. You can look at these at atmosphere. You can change the gas. You can change the temperature. Now all you have to do is really think about the type of materials you want to study. MOFs, zeolites, something that can soak up a lot of the carbon dioxide, something can soak up a lot of the hydrogen, and really understand at a high level of detail what's going on, physical mechanism. Oh, okay. Yeah, so what we're good at in microscopy, we can correlate with theory and simulations like I showed you. We can have directly interpretable images. We can now understand where the atom positions are. We can look at local lattice strain. We can then calculate with our theory folks, all the energy barriers, pathways, and maybe, you know, give us a design rules or criteria. This is something that you'll see a lot more and more. AIF is well equipped with MPAD detector to do 4D STEM. So basically this is a technique where you can take the focus STEM probe, raster through the sample, collect diffraction information as an image, and then you can mine this for a lot of information. We published a paper a couple years ago now, where we're interested in doing picometer resolution strain mapping of bimetallic catalysts for formic acid oxidation. So you take a 4D STEM, we're able to take materials that was synthesized at Indiana from Sarah Skrabolak's lab and come up with a way that we can look at the diffraction patterns, look at the local shifts in the reciprocal space, and then put a measure on that as far as how much strain you have. And the name of the game with catalysis is, you know, how the electronic structure is changing and how strain is changing, because that's going to affect how much of the molecular species that can be absorbed and then perhaps converted catalytically the other way. So just, I know you can't see this too well, but 4D STEM strain mapping, geometric phase analysis, which is take a Fourier transform of this and then see how much is strain, and then also atom position, so we can note the atomic position and look at how it's distorted. My eyes are getting a little bit better. I had LASIK finally a couple years ago, but to me, this data suggests that if you do this 40 stem strain mapping, you can have much better precision in your strain mapping and quantification. So this is important. You can take the same technique and now look at local charge. You know, for example, if you have a 2D material, create a line defect, you can look at the charge distribution. Perhaps it's interesting for quantum materials. Very nice paper out of Grenoble, who were looking at PN junctions in microelectronics and looking at charge distribution under bias. I think you guys have capabilities for that here at AIF. So all these are starting to come to head where you have this latest state-of-the-art electron microscope. You have these great precision machine holders that can have functionality for heat, bias, gas, liquid, what do you want to call it. But the idea is to now use multimodal probes to really pick out more information during an experiment. So your lab in a gap experiment. I drive an old Volkswagen, 1966 Bug that I drive when it's running. But I like to think out the box and I like to think about speed. So the famous thing when I was growing up, it was like the bumper sticker that I saw everywhere in California was 0 to 60 in 11 minutes. I know folks with Teslas would probably hit like 2.7 seconds or 3 point something seconds. But I want to go fast. You want to be able to observe dynamic events at high temporal resolution. A couple years ago, we tried to think out of the box, right, with the spiral scans. I won't go into details because we're pressed for time. So please talk to me if you want to change your way of thinking about microscopy, for example. But long story short, we're able to spin the beam extremely fast, and we're able to unzip a lot of the distortions that take place. This is it right here. This is basically what I wanted to close on is with the microscopes that we have, with the electronics, with how we can tap into the instruments themselves, we can take a high-end performing microscope and do some crazy things with it. So let's change it. Let's see how fast we can spin it, 10 frames per second during this whole transformation process, all the way to 100 frames per second. Now, right away, it's pretty cool because you're increasing your temporal resolution, but you still have enough signal noise to see where all these atoms are going, right, and how they're transforming. So going back to the idea of atomic fabrication, atomic manipulation, let's see it, but let's see it a lot faster. And of course, I want to thank everybody, right? Nobody can do this on their own. This one person in particular, I was very fortunate to have a postdoc, Xiaohan Song, who has some roots in NC State, right? He was I think he was Jim LeBeau's first postdoc, and I kind of poached him away at a coffee shop meeting in a conference. I think Jim was okay with it, reluctantly. But now he did a postdoc with Jim for a year or so. And then he stayed with me for 3 years. Now he's a full professor of Wuhan. So this is a really nice success story. A lot of students and postdocs, a lot of really excellent staff scientists at the lab, and a lot of theory folks that help contribute to this work. So thank you very much for your attention. I'm really happy that you were able to see some of this, and I'll be happy to answer any questions. Thank you.
What challenges do you think you could address to enable atomic layer deposition and things like chemical vapor deposition inside the microscope?
Yeah, that's a good question. So right away, you want to turn towards a dedicated instrument, something that can introduce different reactive gases, something that you can have a stable substrate. Of course, your platforms can be the same with the STEM, for example. You can have the same electron optics, the gun, condenser lenses, all that stuff. But you need a delivery system that you can see that. Couple ways you can do that. You can have a membrane type cell, but I found that sometimes if the membranes are pretty thick, then you're going to degrade some of the spatial resolution. So you might want to look towards dedicated instruments called environmental TEMs that can do that. And it's a little bit of primer, but this summer we're going to spit out an MRS bulletin, a special issue on gas phase microscopy. So I'm one of the guest editors with Eric Stack at UPenn. So you're going to see an article that's led by Frances Ross at MIT, and you're going to see that she teamed up with Kimberly Philander Dick at Sweden, and they've been doing a lot of synthesis inside their microscopes to be able to see things like that. So ALD is very important. I know NC State has a rich history in that. So maybe you can see some atomistics during the process and maybe improve the design process. If you see it, you can believe it, perhaps. Maybe that's the message I should have, the cheesy message I should have started out with, in the first title of my talk.
I really like the heat treatment and the atomic drill bit.
Yeah.
I was just curious for the atomic drill bit, is there any risk when you do that of like bending the whole material? When you...
That's a good question. We're so Maybe, yeah, because you know, the boundary conditions, it's a pretty big material. We're only perturbing a small part of it. We never looked at that. We never looked at that. Just because we're so focused on atoms and seeing them move, we got excited about that. But that's a good question. And perhaps this is a way that engineers strain in these materials, like a far field strain. Maybe you can enhance some property like optoelectronic properties. But thanks for noticing that drill bit. My postdoc and I were going back and forth. Should we actually call it an atomic drill bit with that catch? People excited about that? All right. Yeah, well, he won out. I was trying for something else. So you guys are on the same wavelength, same mindset. So. Thanks.
We try to use the electron beam to generate crystal feedback. How much visibility do you have on the electron energy?
Oh yeah. Yeah.
Have you tried doing it on the salt material?
No, we haven't. Oh, let me go back to this, Frankie, because I think this is pretty important to say. And I'll tell you a funny story. There's always funny stories. There's always backstories and anything in life. So with our microscopes, we can go to 30 kV, 60 kV, 80 kV, 200, and our Titan is at 300 kV. So there's some variability in that. Funny story in this, Beth Hudak did this manually, right? She positioned the beam, she parked it, and it went out for a couple of rounds in science, and they were like, okay, well, changes the kV, how does it affect things? Because you're changing your accelerating voltage. If you're below that knock-on threshold, things are not going to happen. So if you're 30 kV and at 80 kV, then you start to have that energy that kicks out. So that's a big influence on that. And the reviewer said something like, yeah, you need to test that. And when they finally changed the kV, it still wasn't good enough for the reviewer. And I said, just because you didn't put this business atom right here, that's why you didn't get it in science. No, I'm just joking. So there's beam accelerating voltage, and then there's dose. Those kind of work hand in hand. So anybody who does microscopy, first thing you're going to notice is there a beam effect? Is there a dose effect? And that's something that parameter space that people really need to work out. And we were looking at single accelerating voltages and just changing our stand pathway. So we didn't explore that in detail. But people in the soft matter community are very concerned about that. They understand in structural biology, for example, you want to be below like a few electrons per angstrom squared before you destroy your material. So you want to be able to image with that low dose. And that is why the community developed the direct electron detectors. So make every electron count. You're changing your KV, you're changing your dose. You want to be able to see all the electrons that are falling in your detector. So I don't know if that really answered your question, but there's a lot of room to turn those knobs to see what's going on.
Yeah, thank you for the talk. Very, very neat stuff. Since we are on this page, I have to comment on it. Why pay a graphics designer a few $100s if you can buy a $6 million?
Yeah, exactly. So please come with me next time we're writing a proposal.
But the more serious question. So very neat on the machining stuff, particularly. You can say a little bit more on the catalysis issue.
Mm-hmm.
So if you create these holes, these are very active sites.
Yeah.
Yeah. So since they are very active, they like to react. So how, if you use it for catalysis, how do you keep them from reacting?
I got a proposal due on Tuesday for that. I don't.
This is
Yeah.
like a pre-review comment.
Yeah. I always like to say if you build it, they will come. But no, that's a really good question. I guess this is a great opportunity to point to this. So what we want to be able to do in that research is we want to be able to use thermal treatments or hit it with a beam or hit it with lasers to change that structure. We know from the STEM that if you have sufficient energy, you can transform it, right? But we need a way to test the activity. And this is a nice droplet cell configuration where if you have a 2D material and then you can transform it, put the electrode on there, stick electrodes, then you can measure the HER activity. So we haven't done that one-to-one correlation yet. That's kind of like way down the road. I think what we're trying to do right now is just show the concept, show what's experiments in theory, perhaps what's possible in terms of what is the best structure that gives you the most efficient reaction. So I'm light years behind what you're thinking right now, to be honest with you.
Yeah, so yeah, my main concern is catalysis should leave your surface in comfortable state.
Yeah. Right.
But this is going away anyway because the electric cars.
Yeah. Make sure I don't send, you don't review my proposal.
I really like the work on the atomic scale manipulation. Could you say a bit about the outlook? I mean, there's all these things you can do, learn, but it's still a serial technique.
Yeah.
In terms of scaling up.
Yeah, so scaling is a big issue. I like to say that a lot of us at the national labs work on that borderline with fundamental science. It's not really applied at that point. So these are single experiments. What we're trying to do is develop workflows, get people excited about the idea of what can be done, and then transfer that type of knowledge. And that's not a really good answer for what you're saying, but yeah, these aren't difficult experiments anymore, but they are time consuming. And if you're trying to mass produce little metallic elements in a semiconductor, maybe Intel would be interested in that, probably not. I mean, that's a big capital investment to do something like that where, well, maybe not. I mean, you can have like a conveyor belt and move it to the next one, and the next one, and create these little interconnects. But this is just a concept. I'm sorry, I don't really get an answer. Ask me 20 more years, you know. Yeah,
Are there any questions?
Use, you know, the number system, IDES for the electrostatic shutters up in the. Do you see any utility of combining that with the non-orthogonal fast break pattern?
Yeah, absolutely. So we don't have that. We had to build our own. I created that to increase the temporal resolution with those electrostatic thing. I wish we had that, to be honest with you. Yeah, I mean, that's important because if you want to be able to observe these dynamic evolving reactions, there's scan and drift distortion. And I think if you running at the speed of light, for example, there's always going to be distortion. So you got to figure out a way to correct it. Maybe that's something that we can play around with in the future if that comes available.
Okay, time for lunch, and before we thank Ray for coming out and for his talk, I want to present you a little token from the department and a little thank you for coming out here
Thanks.
as our seminar speaker. And with that, I think we thank you for this great talk.
Thank you. I know. How you been?
I will see you.
These meetings are so short, so that's my only complaint. 30 minutes. It's not a lot of time to catch up.
Visit. I'm in a long time in the US. And I told my, like, I wish I could tell you that I got down to some, you know, detail.
Within no time, one after.
Hopefully I figure out, but I'm.
Yeah. I really